So just to start off, obviously we're finished with unit 3, so we're going to start a new unit. Unit 3 was all about trig stuff, and we saw how that all worked out. Obviously, it's in the books now, so whatever you got. I haven't actually looked at the test results, all of them yet, so I looked at it a little bit on Friday, but as always, if you didn't do as well in unit 3 as you wanted, try to do something different on this unit. If you did as well as you wanted, then obviously keep that up for this coming unit. All right. This coming unit, I will say, is kind of 3 different topics thrown together. There are some connections between them, but the 3 different topics it's not one big topic like trigonometry, in other words, or exponential and logarithmic functions or something like that. So it's 3 different topics, and it spans 3 chapters. There's chapter 8, chapter 9, and chapter 10. Okay, we'll get through as much as we can in the next few weeks. Next week is Thanksgiving, so that'll throw some things off, but other than that, we'll be good to go. All right. Any questions about unit 3 or unit 4? What's coming up? All right. So in the first part of this unit, chapter 8, we're going to deal a little bit with the trig stuff that we dealt with last time, but it's not in the context of trig, all right? It's not in the context of using trigonometric functions, okay? It's in the context of polar coordinates. So we're going to look at some polar coordinates. We already know that any point on the unit circle can be written as cosine of theta comma sine of theta, where the x value, so that's going to give us a point on the unit circle. Therefore, the x value on the unit circle is cosine of theta. The y value is sine of theta. Okay. We already, again, have established that. Well, the question is, what if we scale that circle up? If we scale that circle up, then all we're going to be doing, or down, we could scale it down or up, then all we have to do is change the radius of that circle. So any point on some circle of radius r can be written as r cosine of theta, comma r sine theta. And if you think about what that means in general on the Cartesian coordinate plane, any point on the Cartesian coordinate plane is going to be some radius distance away from the origin, right? It's going to be on some circle of radius r for some value of r. Okay. So any point in the Cartesian coordinate plane can be written as r cosine theta as our x value and r times sine theta as our y value. So any point can be written that way on the unit circle, or excuse me, in the Cartesian coordinate plane. where the x value is our sine theta, the y value is our sine theta. And this is what polar coordinates does. It says since any value, or since any point which is an xy point, instead of thinking of the x value of that point and the y value of that point, let's think about what the radius is of the circle we would need. And let's think of the angle from the x-axis and what angle we need to get to that same point. So instead of giving us x and y, polar coordinates are going to give us r and theta. We follow that? So polar coordinates are giving us r and theta. And our standard xy coordinates, we call rectangular coordinates. We call them rectangular because you're moving in rectangular shapes, left and right, up and down. Those grid out in rectangular shapes. Does that make sense when I say rectangular shapes? Up and down, left and right. So polar coordinates give us the r and the theta needed to get to the point. Rectangular coordinates give us the x and the y to get to the point. And like we just said, because we can scale out the unit circle with any radius, anytime I have rectangular coordinates, x and y, I know they're going to be connected to polar coordinates because x is going to be r times cosine of theta. And y is going to be r times sine of theta. Well, what else do we know? We know in right triangles, the tangent of theta is going to be y over x. By the way, cosine of theta is going to be x over r. That's just a rewrite of this first one. You divide both sides by r. That makes sense. So I'm talking about SOHCAHTOA here. So the tangent part of SOHCAHTOA gives us y over x. The sine part of SOHCAHTOA would be sine of theta is equal to y over r, but that's just a rewrite of this y equals r of sine theta. Same deal. And then the last is the Pythagorean theorem. The Pythagorean theorem on a right triangle would, on this right triangle, would say x squared plus y squared is equal to the radius squared. All right. So when we're converting back and forth between polar coordinates and rectangular coordinates, I have these four equations that I'll be using. If we're given polar coordinates, then I can just plug in the r and the theta into r cosine theta. That'll give me my x value. I can plug in the r and the theta into r sine theta. That'll give me my y value. If I have rectangular coordinates, I want to find the polar coordinates. That means I have the x and y. I want to find the r. I can use the Pythagorean theorem equation. If I want to find the angle theta, then I can use this tangent equation. Okay. So let's do a couple of conversions. Let's say I have the following polar points. Again, When we're writing polar, we always write the r first and then comma the theta next. So it'll always be radius, comma, angle. Here we have 3, comma, pi over 6. And 7, comma, 4 pi over 5. 2, comma, negative pi over 8. And then negative 2 times 7 pi, not times, comma, 7 pi over 8. And we want to convert those points into rectangular ones. These are the 2 equations that we're going to use. All right. So there they are. And so the rectangular coordinates here for 3, comma, pi over 6 are going to be whatever we get when we take 3 times cosine of pi over 6. That'll be my x coordinate. My y coordinate will be 3 times sine of pi over 6. Let me write it this way. So this is going to be our rectangular coordinates. In this case, we actually know what the sine and cosine of pi over 6 are. Cosine of pi over 6. Oh, shoot. You know what I did? I did something wrong. I had my calculator still in degree mode. Make sure your calculator is in radian mode. We are using radians here. But cosine of pi over 6 is that 0.866. That's root 3 over 2. So we would get 3 root 3 over 2. Because cosine is square root of 3 over 2. And then sine is 1/2. Sine of pi over 6 is 1/2. So we get 3 over 2, or 3 times 1/2. As my y value. I'll leave it like that. Moodle, you can round to 2 decimal places or something like of that. So okay. So it's just that straightforward. It's just plug in r cosine theta. That'll give you your x value, and then the y value will be given by r sine theta. Okay. On these next ones, these are not going to be nice angles that we have memorized like the previous case. So on these ones, when I type things in, 7 cosine of 4 pi over 5, and then 7 times sine of 4 pi over 5. I'll have to use decimal versions, okay? Round to a couple of places. In this case, notice that the x value I got was negative 5.66, and the y value I got was a positive 4.11. By the way, this should all make sense in terms of locations. If you think about the angle 4 pi over 5, that's just a little bit under pi, so a little bit under 180 degrees. Does that make sense? Point in this this direction, and we're pointing out 7 units in that direction, and we're going to get a point somewhere in that region. We're going to get a point in the second quadrant, is what I'm trying to get at. So it has a negative x value and a positive y value. Okay. Our first one, pi over 6, that was in the first quadrant. That was an angle in the first quadrant. So we should have expected to get positive x and y values. Okay. Here, 4 pi over 5 points into the second quadrant. So we should expect to get a negative x value, positive y value. I want you to try these two on your own. Now, hopefully what you notice about this, again, I'm just typing this into my calculator, making sure the calculator's in rating mode. It's that you get the same rectangular point. We get 1.85 roughly, comma, negative 0.77 roughly. Okay, when I round to 2 decimal places. So we get the same rectangular point even though our polar points were not identical looking. Okay. It gave us the same rectangular point even though the polar points were not identical looking. And you can kind of intuit that based on a few different things. First, in this first point, we're talking about an angle of negative pi over 8. So we're pointing down in this direction. Right, negative pi over 8. Down and to the right. So it makes sense that this is in quadrant 4. Right, positive x, negative y. On the second point, we started with angle 7 pi over 8. That's actually the angle here. Trying to draw an arrow there. Which is 180 degrees or pi radians away from negative pi over 8. But I used a negative r. If I were to use a positive r, I'd be in the second quadrant. Using a negative r means that I go in the opposite direction and I end up in the exact same place I was at earlier. Did I get that? So that's why these 2 points gave me the same rectangular point. And once you see that, then you'll realize, well, that can happen in a lot of different ways. Here we had negative pi over 8. What if we said, let's talk about an angle between 0 and 2 pi? We could have added 2 pi to that. That would be, what's that, 15 pi, no. Yeah, 15 pi over 8. Is that right? If I add 2 pi to negative pi over 8. I could have added another 2 pi, any coterminal side, any angle that's coterminal to negative pi over 8. If you put 2 comma coterminal angle, you're going to get back to the same point. So you can just add 2 pi as often as we want and get back to the same point. Same thing here. If I have a negative 2 and then any coterminal angle with 7 pi over 8, I get back to the same point as well. Does that make sense? Now, this is not a problem for us. That's not a big deal, going from polar to rectangular. When I go in the opposite direction, I'm going to have to specify what angle I want to use. Okay. And that's what we'll do in this situation. So now let's go in the opposite direction. Let's take some points like 2, 9, and negative 3, 5, and 8, negative 2, and negative 5, negative 7, and get the polar version of that. So starting with rectangular and going to polar. Now, when you're writing this in your notes, leave yourself some room because we are going to have to do some algebraic work. I'll do the 8 negative 2. I'm going to use that. So I have them all written down. It's not big. Now, the equations I used to go from polar to rectangular were these two. The ones that I used to go from rectangular to polar, generally speaking, are the other two. The one that is the Pythagorean theorem, and the one that says tangent of the angle is equal to y over x. Those are the two that I'm going to use to go from rectangular to polar. So let's take 2, 9, for example, and let's use those two equations. The first is the Pythagorean theorem, 2 squared plus 9 squared is going to be my radius squared. That's 85 is equal to the radius squared. So the radius is the square root of 85. Is that right? I almost always use the positive radius technically, we saw in the last example, you could also use the negative R. But usually, when you convert into polar, you use the positive R. That's the standard. Now, to get the angle, the tangent of the angle is going to be 9/2. That's y over x. And this is where it gets a little bit tricky. Remember that tangent inverse on our calculator is defined in the first quadrant and in the fourth quadrant. So tangent inverse is going to give me an angle in either quadrant 4 or quadrant 1. That's perfectly fine for 9/2. In this case, because 2,9 was in quadrant 1. So since we're in quadrant 1, theta is just going to be the inverse tangent of 9/2. And that's something I can type into my calculator. I'm in radian mode. That gives me about 0.35 radians. How do I want to write this? I'm going to write this in 2 ways. Also, square root of 85 is about 9.22. So my point is about 9.22 comma 1.35. That would be the point in polar form. Is that right? Good. Now let's do a similar thing for -3,5. So for -3,5, when I use the Pythagorean theorem, I think that's 34. And square root of 34 is your R. I'll wait to write the point till the end. And then tangent of theta is going to be the y value divided by the x value. That's 5/-3. Now, I want you to notice that -3,5 is actually in quadrant 2. So -3,5 somewhere in quadrant 2. But tangent inverse is not going to give me something out that's in quadrant 2. It's going to give me something out that's in quadrant 4 or in quadrant 1. You understand that? What do you think it's going to get me out? Yeah, the quadrant 4, that forms a straight line with this. Okay. So all I have to do is add pi to whatever it gives me out. That's what I'm trying to get at. So since my point is in quadrant 2, my theta that I'm going to use is pi plus the inverse tangent of 5/-3. So the polar point is approximately, well, square root of 34 is about 5.83. That's your R. And then your theta is about 2.11. Is that right? You could also write square root of 34, comma, pi plus inverse tangent of 5 over -3. By the way, the reason why another reason why I know we dealt with this when we talked about inverse trig functions, but I'll say it again. When I tell my calculator to take inverse tangent of 5 over -3, it's going to calculate -5/3, which could have been either obtained, -5/3 could be either obtained by using this point, -3 comma 5, or it could have been obtained using this point, +3 comma -5, right? So it has to choose one, and with the definition on our calculator, it always gives us the quadrant 4. Quadrant calculator always gives quadrant 1 and quadrant 4. If you're in quadrant 2, you have to add pi. If you're in quadrant 3, you also have to add pi. Does that make sense? All right. I'm going to erase this, and I want you to try to do the same thing for these next 2 points, 8, -2, and -5, -7. So we have 2 rectangular points, and we want to convert those into polar points. Try that on your own. Get the R and theta for each. All right. So once you've done these a few times, it goes pretty quick. Let's do the 8, -2. 8, -2. Use Pythagorean theorem to get that r is equal to the square root of 68. We can get a decimal version of that if we want, but I'll just say square root of 68 right now. And then the tangent of theta is going to be -2/8. I don't need to reduce that if I don't want to. By the way, the point 8, -2 is down in quadrant 4. So the point is in quadrant 4, and that means that theta is just going to be the inverse tangent of -2/8. And that is -0.24 roughly. Okay. -0.24 radians. So in polar form, this point would be, again, the exact value would be root 68 comma inverse tangent of -2/8. But the approximate value, the one you type into Moodle, is 68, 8.25 roughly, comma, -0.24 radians. So radius is about 8.25. And angle is about -0.24 radians. Now I want to just do a note here. Oh, it's a positive R value. Correct. Between 0 and 2 pi. Shoot, I thought I had something different. That's fine. That's fine. Let me, I'll look at this later today when I have some time. But this is saying write your angle between 0 and 2 pi. Obviously, my angle is a -0.24 right now. If you wanted to put your angle between 0 and 2 pi, just add 2 pi to it. Does that make sense? So if you want to force your angle between 0 and 2 pi, that was probably a mistake on my part. I probably wanted to go from -pi/2 to +3pi/2, but even in any case, 0 to 2 pi. I'll talk about that next time if needed. But everybody understand that if you end up at -0.24, just add 2 pi, and then you'll be at an angle between 0 and 2 pi if you want that. It's that one. Oh, it doesn't talk about it. That's fine. All right. So if I want an angle between 0 and 2 pi, let's add 2 pi to it. That'll be coterminal, and then we'll be done. I'll leave it right like that for right now on your notes. In terms of this second point has radius of square root of 74. The point is in quadrant 3, -7, -5, somewhere in quadrant 3. I know my angle is going to get me into quadrant 1, so I'll have to add pi to it to get that. So since we're in quadrant 3, my angle is going to be pi plus the inverse tangent. I could write -7 over -5, but the negatives will cancel out. I'll just write 7 over 5. And then I'll give the approximate values here. I guess since I did exact, I'll do exact too. Exact would be √74, comma, pi plus inverse tangent of 7/5. That would be the exact value. Square root of 74 is about 8.60. Pi plus inverse tangent of 7/5 is 4.09. And by the way, when in doubt, think through where 4.09 is. That's between pi and 3 pi over 2, right? So we are in the correct quadrant. That makes sense. So we are in the correct quadrant with 4.09 radians. We okay with that? That conversions, doing conversions. Now what we're going to do is we're going to deal with equations in polar form. Okay. So the advantage of polar form, we're going to see in just a moment. There are advantages and disadvantages. I should say that. I don't want to make you think that polar form is always the best form. It's not always the best form to use. But sometimes it is. Sometimes it's not. So let's take and graph something in polar form. Now, one thing we can do, if we have an equation in polar form, usually the standard is that we write r is equal to a function of theta. Just like the standard in rectangular form is y is equal to a function of x. The standard in polar form is r is equal to some function of theta. So like in this case, r is equal to 2 times theta. And we could set up a table with a bunch of r values and a bunch of theta values. And it could give me a graph. So for instance, if I put theta of 0, then 2 times 0 would be 0, r would be 0. If I put a theta of, let's say, pi over 2, then r would be twice that amount. So that's just pi. If I put in a theta of pi, then r would be 2 pi. If I put in a theta of, let's do 3 pi over 2, then r would be 3 pi. If I put in a theta of, let's do 2 pi, r would be 4 pi. Let's do just one more. Let's do 5 pi over 2. So plug in 5 pi over 2, r would be 5 pi. Okay with that? The calculations here are just multiplied by 2. So it's pretty straightforward calculations. in that case. I'm not gonna go to find pi. All right. Now let's think about all of the points that we just graphed. This is saying if I'm at theta of 0, that's angle pointing this way, then my radius, how far away I am from the origin, is going to be 0. So 0, 0 in polar coordinates is my origin. Same as in rectangular coordinates. Then let's go to angle pi over 2. If we're in angle pi over 2, we're pointing up. We're going to be pi units away from the origin when our angle is pointing up. Do you understand that? Now I have to do a measurement of pi because I'll screw it up. So I was trying to get a, maybe this will work. Let's say pi is 1 eraser width. So I'll just make it pi units up, about right there. Okay. Now when we're at angle pi, we're 2 pi away from the origin. So when my angle is pi, we're pointed that direction. I am 2 pi away from the origin. I'm somewhere in here. So I started here. Technically, we go up this way a little bit, round out there. At angle 3 pi over 2, I am 3 pi units away from the origin. So somewhere in there. At 2 pi, I'm 4 units away. Trying to do this fairly accurately. Okay with that? 2 pi, we're moving, pointing straight out. And then 5 pi over 2 is coterminal with pi over 2, right? Notice that we get a different value for r in that case. We get 5 pi. I'll try to do this 1, 2, 3, 4, 5. Like that. And we can move on, we can go on from there. Okay. If you connected the dots and then added more points, what you see is that we get a shape that spirals out. And then this would keep going. Right? And it would, you could spiral it, you could continue for forever. That spiral would go on and on and on and on. Now here's a trick question. Is this a function? It said it's a trick question. So I could either say, the answer is, it depends. In the rectangular coordinate system, this is not a function. It fails the vertical line test in the rectangular coordinate system. But in the polar coordinate system, r is a function of theta. So this is a function in the polar coordinate system. It is not a function in rectangular coordinate system because it fails vertical line test. So if you try to create an equation with x's and y's that did this curve, it'd be a really, really ugly equation. It'd be a very ugly equation. This one, not so bad. Does that make sense? By the way, I'm going to show you in a moment on your calculator how graphs work with polar coordinates. But on Desmos, if you just type in, for instance, r is equal to 2 theta, by the way you get theta is you just type in the Greek letter, the Greek word theta, T-H-E-T, and then when I hit the A, it translates that into the Greek letter theta, right? And you see what happens. You get this spiraling effect. This is, it's stopping right here because theta is going from 0 to 12 pi because I don't know why, but that's what Desmos did. If I went out to 6 pi, it would only spiral around a couple of times. And if I went out to like 36 pi, it spiraled around more times. Okay. But you can see that if we go to infinity, then we get an infinite spiral pattern. Does that work? So we can graph these things in Desmos, and we'll see a little bit later. We can also graph these things with graphing calculators. Right. Now, before we start graphing lots, now we can see that, well, let me state. Now we can see there is an advantage to having polar coordinate system. We can get these graphs, which are kind of inaccessible, via the rectangular coordinate system. On the flip side of that, some graphs in the rectangular coordinate system can be translated easily into the polar coordinate system. Others are not going to be easily translated into. So some graphs are going to be easy to translate, some graphs are not. If I'm going to ask you to convert an equation from rectangular to polar, it'll be something that can be done in a fairly straightforward manner with a little bit of algebraic trickery. So for instance, let's look at the following two equations. And let's say we want to convert the equations from rectangular into polar. We have x squared plus y squared is equal to 144. And then x is equal to 7. Now I erased my equations earlier. But I'll write them back down. There they are. I'm going to use those four equations to substitute. Now, if we're going from rectangular to polar, we can always substitute every x I see with an r cosine theta and every y I see with an r times sine theta. So let's do this one first. Is that right? If I'm doing this one first, then I just say, oh, there's an x there. So let's substitute r cosine theta for my x. And now I have an equation involving r and theta. Now, like I said, generally speaking, we usually write polar in this format where r is equal to a function of theta. That's the standard format for polar equations. Just like y is equal to a function of x is the standard format for rectangular equations. Not all polar equations can be written this way, but if we can, we'd like them written that way. So what I'm going to do is I'm going to divide both sides by cosine and get that x equals 7 in rectangular form is r equals 7 divided by cosine theta in polar form. Okay, that. So when in doubt, we can just replace each x we see with r cosine theta, each y we see with r sine theta, and then solve for r. And that gives me an equation in polar form where r is written as a function of theta. Now I could do that over here as well. I could replace the x with r cosine theta. I could replace the y with an r sine theta. But in this scenario, I can also use this third equation. Since I have x squared plus y squared on the left-hand side, I could just replace that with an r squared. And then usually what we do is we'll take the positive square root of both sides, and that'll give me an r equals 12. By the way, this is a circle of radius 12 centered at the origin, written in rectangular form. So that means this is a circle at the origin, sometimes called the pole, written in polar coordinates. Notice that this is a really easy equation to deal with. It's just r equals a constant. And it turns out that if you go on to calculus and calculus 2, utilizing polar coordinates when doing things called derivatives and integration sometimes can be a lot more effective than staying in rectangular form. Right? Because we get things like circles, which are kind of hard to deal with in rectangular form. Sometimes they're really easy to deal with in polar form. Very simple equations in polar form. So there you go. By the way, if somebody else said, actually, I wanted to replace the x with an r cosine theta and the y with an r sine theta, what's going to happen is you get r times cosine squared of theta plus r times sine squared of theta equals 144. You could have r squared, excuse me. I have to square the r and square the cosine. Square the r and square the sine. Right, that way. I could have factored out the r squared on the left-hand side. And then what would have happened is I would have been left with cosine squared plus sine squared on the inside of parentheses, which we know from our trig identities is 1. Right? Cosine squared theta plus sine squared theta, trig identity, that's 1. And therefore, I get r squared equals 144, which means r is 12. Notice that that's a little bit more difficult than just replacing the x squared plus y squared with an r squared. So that's why we did it the way we did it. Any questions about that? So, as usual in mathematics, use the easiest tool. You can see that x squared plus y squared can be replaced with r squared. Use that. That'll be the easiest replacement. And then, there you go. I want you to try these two on your own. And then if you can, on each of them, when you convert into polar, solve for r. Write the polar equation as r is equal to a function of theta. Does that make sense? Get the r on the one side by itself. Try these two on your own. All right, let's go through these. In both of these, we don't have the x squared plus y squared, so there's negative r squared replacement. So when in doubt, turn to replacing every x we see with our cosine theta and every y we see with our sine theta. R times sine of theta, all squared, will be equal to 36 times r times cosine of theta. Now on the left-hand side, when I square it, I'll get the r squared, and I'll also get a sine squared. What I would do is I would divide both sides by r, and then divide both sides by a sine squared. On the right, these r's will cancel. One of the r's on the top will cancel with this r on the bottom. So I'll just get a single r on the left. The sine squareds will cancel. And I'll get on the right 36 cosine of theta divided by sine squared of theta. Okay with that? And that's it. That's the whole thing. So this is a parabola. And rectangular, this is that same parabola in polar. Parabolic shapings. By the way, this parabola is one that's pointing to the right, just so that you know, pointing to the right. It does this. That makes sense. Not that you need to know that, just FYI. Now on this one, I would do the same thing to start out with. Replace the y with an r times sine of theta. Replace the x with an r times cosine of theta. That minus 2 there, if I try to, well, if I try to solve for r the same way I did in my previous equation, it's not going to work. Okay, I can't just divide. There's not going to be a canceling out nicely. We could, but it's going to be more difficult. There are a couple of different ways to solve for r here. I'm going to show you the way that I like most, but I'll also, after that, show you the way that I like second most. That's all right. So we just need to solve for r. What I would do is since all of my r's are only occurring once, I'm going to subtract 3r cosine theta from both sides. That'll give me r times sine of theta minus 3r times cosine of theta is equal to -2. So I have all of the terms with r on the left-hand side and all of the terms without r on the right-hand side. Now I can factor out the r on the left-hand side. that'll give me this. 3 times this number, sine minus 3 cosine, is equal to -2. In order to solve for r, I just need to divide both sides by that number. Okay with that? So I know it's a big, messy looking number, sine theta minus 3 cosine theta, but that is still just a number. So just divide by it on both sides. And we get r is equal to -2 divided by sine of theta minus 3 times the cosine of theta. So that's the way I like to solve for r. That's my favorite technique. Get all the terms with r's on one side, all the terms without r's on the other, and just factor out the r, divide by whatever this number is. There is another method that we could have used to solve for r once we get down to that stage where we had r times sine of theta minus 3r times cosine of theta. Oh, no, wait. Sorry. Let me go back to the previous stage. Sorry. R sine theta equals 3r cosine theta minus 2. So right after we plugged in the x and y equivalents. So the other thing we could have done at this stage is we could have divided everything by r, giving me sine of theta is equal to 3 times the cosine of theta minus 2 divided by r. And then I could have subtracted 3 cosine theta from both sides. On the left, that would have given me sine of theta minus 3 times the cosine of theta equals -2 over r. And then there's a couple ways you can think of this. You can think in terms of reciprocals, take the reciprocal of that, set it equal to the reciprocal of that, and then multiply both sides by -2. Or you can think multiply both sides by r and divide by that number. Either way, it's fine. I'll use reciprocals now. Just make it. You see, you're going to get the same thing, but. So if I say, well, these two are the same, when their reciprocals are the same, then I get that equation, and then I can multiply both sides by a -2. Again, same exact equation. So that's another way of solving. And if you prefer that way, you can use that way. Not that big of a deal. If you prefer this other way, I kind of gravitate towards this way, where I factor out the r, get all r terms and then factor them out. You can do that as well. But again, both lead to the same equations. Okay. Now what we can do is we can do the reverse. We can go from polar to rectangular. This one is a little more difficult. This one takes a little bit of finesse. The reason why these take a little bit of finesse is because of how our equations are written. When we had rectangular systems, when we had rectangular equations, when in doubt, I could have always replaced the x with r cosine of theta. And I could have always replaced every y I saw with r sine theta. But if you look at this polar equation and you say, well, what can I replace sine of theta with? It's not so easy. Technically, I can try to replace theta with the inverse tangent of sine, or excuse me, of x over y over x, excuse me. But then I'd have to take the sine of inverse tangent of y over, it'd be tough. So when we're dealing with polar and we're trying to go to rectangular, what I would like to do is I would like to have things that look like r cosine theta, or r sine theta, or r squared. In this first equation, what I would do to get what I want is I would multiply both sides by sine of theta. If I multiply both sides by sine of theta, I get r times the sine of theta is equal to 6. And that's great because r times sine of theta in rectangular coordinates is just 1. So now I have a y equals 6 in rectangular coordinates, and I'm done. Now, we may think, okay, from that one, I should just try to get all of the trig functions on the same side as the r. If you try to do that with this one, I would have to divide by cosine. So don't write this down. If you divide it by cosine, you'd get r divided by cosine is equal to 10. That is not something that you can use from over here. Okay. R divided by cosine is not a polar conversion. So in this case, I have to use a different tool than what I did here. Also, well, let's get the tool. What tool should I use? Anybody see? to get something like r cosine theta, to get something like r sine theta, to get something like r squared, or to get something like tangent of theta. See it or not? That's fine. Keep going. The key thing here is to multiply both sides by r. Okay. If I multiply the left-hand side by r, well, I guess I can write this again. And then multiply the right-hand side by r. The left-hand side is going to become r squared. The right-hand side I can write as 10 times r times cosine of theta. R times cosine of theta, I can replace just with an x. R squared, I can replace with an x squared plus y squared. So we get x squared plus y squared is equal to 10 times x. By the way, this is going to be a circle if you actually drew it up. It won't be centered at the origin. It'll be centered at, what is it? 5, 0, I think. Yeah, 5, 0. But that's what it is. By the way, when we converted everything into polar, we said let's write the standard version, r equals a function of theta. When you convert into rectangular, we will not solve for y. The standard version of y equals function of x, we won't do. Right? So we'll just leave it alone. This would be my final answer. And then we move on. That's what you plug in, type in, and move. Try these two on your own. Convert each of these two equations from polar to rectangular. All right. So let's go through these. With r equals 11, the technique we're going to use, the easy technique, is to square both sides. So we're going to square both sides. That'll give r squared is equal to 121. And then the r squared can be replaced with x squared plus y squared. So we get x squared plus y squared is equal to 121, which we probably expected because we've seen stuff like that before. On this equation, maybe I'd start out by multiplying both sides by the sine of 2 theta. Can I write y equals 1 now? No, right? The angle there is 2 theta, not theta. So I cannot write y equals 1 because the angle is 2 theta. Now this puts me at gives me a slight problem. Okay. I could apply some trig identities, which let's go ahead and do that. Let's apply a trig identity. Sine of 2 theta is 2 times sine of theta times cosine of theta. So I have one r that I can pair with sine, but I don't have another r that I could pair with my cosine. What would happen if I multiplied by r on both sides? If I multiplied by r on both sides, I'd get the r I needed on the left, but then I'd have this extra r on the right that I can't get rid of easily. I guess I could multiply both sides by r and then square everything. I might lose some information. You guys know what I mean by that? Lose some information because you square both sides. Or I might gain some information. So I could do that. I could multiply both sides by r. Then square the left-hand side. Square the right-hand side. Let's put the right-hand side squared. Is that right? I'll show you what's going on here in a second. We're going to get 2 times y times x, quantity squared, equals x squared plus y squared. I could do that, I guess, if I'm willing to have everything be squared. Now, there is some information that I'm going to be losing here, and I won't go too into depth, but there are situations in which cosine and sine are both negative. That I might be having x and y values that work here, that might not work here, or vice versa. But basically, that's the same thing. Is that right? Now, this one's pretty difficult. So very difficult to see. Multiply it by an r and then square both sides. So we had to do both techniques. Those are the two most popular techniques. By the way, if I graph this thing on Desmos, what would this thing even look like? I'll graph it in rectangular here. 2y squared times x squared is equal to x squared plus y squared. I get this weird looking shape there. You see that? So it's basically kind of in all four quadrants moving around that way. Was this equal to 1? 1, yeah. There's the circle right in the middle. It doesn't ever come and touch that circle. But see what's going on. That's the picture. Weird, right? Weird shape. Weird looking shape graph. Obviously not a function in terms of x's and y's. X is not a function, or y is not a function of x. Fails the vertical line test a lot. So yeah. But weird situation there. Weird situation. Yeah, we got time. Try these two on your own. Go from polar to rectangular in these two cases. Both cases, it'll take some algebraic rewriting. Not as much as our previous case, though. No trig identities that we have to apply on this one. Not unless we want to. Extra off. Oh no. Yeah. Wow. Now. Square. That one. Then for coding, that one. Okay. That's it. You have the almost. Oh. All right. People are doing all right. Let me go through each of these. So in this first one, how do I? There's a number of different first steps we can take. I'm going to multiply both sides by cosine squared. Okay. So r times cosine squared of theta is equal to 5 times sine of theta. I have an r times cosine of theta and then an extra cosine of theta without an r on the left. And I have a sine of theta without an r on the right. So I need another r on the left and another r on the right. So I can multiply both sides by r and get that. I'll get r cosine theta times another copy of r cosine theta. So r cosine theta, I'll get that twice. And then I'll get 5 times r sine theta. If you'd rather write this in a different way on the left, like r cosine theta times another r cosine theta, that's fine too. Or r squared cosine squared, that's all right too. But the point is that now on the left, I have r cosine theta twice, so that's x squared. On the right, I have 5 times r sine theta, that's 5y. So I get x squared is equal to 5y. So we have a parabola This one is a parabola pointing up. If you recall, this was kind of like an equation that we got earlier with a parabola pointing to the right when we converted the other direction. So that's it. That's the final answer. Remember that for converting into rectangular, I don't expect you to solve everything for y. So I just leave your answer as this. Now on the next one, we're going to square both sides. R squared is equal to the cotangent of theta. As long as cotangent is positive, we're good to go. So R squared is equal to cotangent of theta. And then essentially I'm done because R squared is equal to x squared plus y squared. And cotangent of theta, well, we know how tangent and cotangent are related. Cotangent and cotangent, tangent and cotangent are reciprocals of each other. So I know we always said tangent of theta is equal to y over x, so we keep saying that. But it's just as true, as long as we don't have 0 in the denominator, that cotangent of theta would be the reciprocal, which is x over y. So figure it that way. Another way I could have done that, so this is the quickest way, right? That's the quickest way. Another way I could have done that is rewritten cotangent as 1 over tangent. And then for my tangent, put in y over x. But 1 divided by y over x is the same thing as x over y. Did you get that? So I could have went from here to here, and then did this. That's x over y. So that's another way I could have done that. That's just given me a couple extra steps, though. That. So whichever way you want to do it, whether you want to see, oh yeah, cotangent has to be the reciprocal, so it has to be x over y. Or if you do cotangent as the reciprocal of tangent and then plug in y over x for tangent, that's fine too. But you have a good feel for converting between polar and rectangular back and forth. Now, let me state a few things. First off, I mentioned this before, but I'll mention it again. Some equations are a lot simpler in polar form than rectangular form. I would argue this one's a lot simpler in polar form than it is in rectangular form. Okay. Some equations might be a lot simpler in rectangular form than they are in polar form. Right? I would argue probably this one was easier to understand in rectangular than in polar. And what I haven't touched on, but is also true, is that some equations in polar form, it's nearly impossible to convert back into rectangular form. If you tried that, it'd be extremely difficult. And it'd be extremely messy. Okay. So there are certain instances where converting from rectangular to polar gets extremely messy. And vice versa. When you go from polar to rectangular, you can get extremely messy or nearly impossible. Some are essentially impossible. So it's nice to have both because, again, some equations exist nicely in polar, don't exist nicely in rectangular, and vice versa. Some equations just simply don't exist at all. So the last thing that we're going to do with these polar coordinate systems is talk briefly about graphing. We already graphed one equation. We graphed r equals 2 theta, and we got that infinite spiral, right? We did that on Desmos, and we also originally plotted points, plotted polar points. Oh, there's a typo there, or didn't. Excuse me. There we go. Now, there's a number of ways we can graph. We can plot points like we did earlier with r equals 2 theta. Another method would be to convert from rectangular or from the polar version into rectangular and graph the rectangular version. But the third option is the one I want to focus on, and that's using technology. All right. So we're going to use our graphing calculators to graph certain things in polar form. We'll graph these things. R equals 6, R equals 5 sine theta, R equals -8 cosine theta, R equals pi over 3, not R. Theta equals pi over 3, theta equals 7 pi over 6. Oh, wrong button. There you go. All right. Didn't work very good, but that's okay. By the way, I did this with the weird one we had where it was like r equals 1 over sine of 2 theta. I already did that. Remember how they got that weird shape? So I did that on my calculator just to see what kind of shape it was going to come up with while we were working on that. It came with this. Obviously, some of the asymptotes are drawn, but that's what's going on. All right. Now, here's the easy way on a graphing calculator to do this. All we're going to do is change what mode we're in. We go from function mode to polar mode. Okay. And then I hit the y equal, well, then you can go to home if you want. And now I want you to notice that on the variable button, it had X, T, theta and n. Right now, if you hit the variable button, because you're in polar mode, it's going to give you the variable theta. Right? Just like when we were in rectangular function mode, it would give me the variable x. Now it gives me the variable theta. And when I go to my y equals, all of the graphs are going to look like r equals and then some function of theta. Now, I've already, like I said, graphed earlier, 1 over sine of 2 theta. This is also one we saw earlier, r equals 2 times theta. So I take 2 and then again my variable button. If I zoom standard this one, standard zoom that, you see that spiral shape. Okay. I'd have to zoom out, but it'd go further. If I want to do r equals 6, graph that. We already know what that should look like. That should be a circle of radius 6. That's what we get. But I want you to notice, because you're using a screen that is longer than it is tall, my circle has been stretched out a little bit, all right? So it's not a perfect circular shape because of the way the screen works. It's longer than it is tall. Does that make sense? So each unit in the x direction is slightly bigger than each unit in the y direction. So it looks like a circle stretched out, even though that's actually a perfect circle. If you want a perfect circle, one way to do that is to do the square zoom on your calculator. And if you do the square, it'll make each x distance the same as each y distance. And now my circle actually looks like a circle, not an ellipse, an elongated circle. Is that all right? So it's as simple as that. The other things we were asked to graph were 5 times sine of theta, 5 times sine of theta. Notice that's a circle that touches the origin, but goes up along the y-axis. The center of that circle is actually 2.5. You can see that. So if we have 5 times sine of theta, the center is 0, 2.5. Okay. If I change that 5 to a 9, what's going to happen is now the center is going to be at 4.5, and it's going to touch the origin. Okay. If I change that 9 to a -9, now the center is going to be at 0, -4.5, and it's going to touch the origin. So it's going to be on the bottom half of the y-axis. If I were to change that sine to a cosine, now it's going to be a circle laid out along the x-axis. It's a negative coefficient. It's on the negative side of the x-axis. If it's a positive coefficient, like +8, then we're on the positive side of the x-axis. Center here would be 4, 0. So you can see there's a number of different ways I can get circles. I can get circles using just r equals a number. I can get circles by coefficient times sine of theta, or coefficient times cosine of theta. Now, make sure you're in radian mode because we're going to be using radians here. Oh, shoot. Forgot to mention this. With the TI-84, everything that you do in polar has to start with r equals some value. We also had graphs that said theta equals a value. Theta equals pi/3, theta equals 7 pi/6. Those really can't be done with the graphing calculator. Not in any easy format, but I did want to cover what these are because they are kind of the building blocks for the polar form. So if somebody said graph theta equals pi/3, we'd say, oh, pi/3 is this angle. Theta equals pi/3 is a line through the origin. Everybody get that? So pi/3 is this angle. And you can be at any radius you want. So you get all the points at that angle, both with positive r values and negative r values. Okay. The same thing is going to be true for any theta equals, let's say it was 7 pi/8. 7 pi/8 would be like this angle. And so we get a line through the origin. Theta equals angle is always going to give me a line through the origin. One note about graphing and the language that we're going to use, that we can use. What's this axis called? In rectangular coordinates, it's called the x-axis. It's often called the polar axis. And polar coordinates, because that's where you start with angle 0. Look at that. This is called the y-axis in rectangular coordinates. And in polar coordinates, we often call this theta equals pi/2 for the obvious reason that it's theta equals pi/2 line through the origin. So the y-axis is also called theta equals pi/2. Sometimes the origin is still called the origin in polar coordinate systems. Other times we call it the pole. So you might say origin or pole. That's where we start everything. Is that all right? So if you see things like this, like polar axis, theta equals pi/2, hopefully that doesn't throw you off. Hopefully those things are pretty straightforward. Pole and origin. Okay. Okay. All right, so we solved some circles. And like I said, we solved 3 different ways to draw a circle. R equals A times sine theta, R equals A times cosine of theta, where A is just some number. R equals A is a circle with radius A, but R equals A sine theta is radius A over 2. Makes sense? Sweet. So, if A is positive. And if it's sine, it's along the y-axis. If it's cosine, it's along the x-axis. And then we also solve this. Anytime we have theta equals some angle, then that's a line through the origin. Or sometimes the line through the pole, P-O-L-E, like I mentioned a second ago. Sometimes people will graph using polar coordinate graphing paper. Have you ever seen that? Or a polar coordinate grid. And since R equals number and theta equals number are sort of the building blocks of polar form, the grid will look like a bunch of R equals numbers, bunch of concentric circles around the pole, and then also a bunch of lines through the origin, oftentimes at our common angles. So oftentimes, if you look up polar graphing paper, you'll get something that looks like this. Coordinate system. And then you can plot any point by knowing the R and the theta value. If I know R is 3 and theta equals pi over 4, I go out 3 circles. Pi over 4 is this angle, so I put the point there. But get that? And then so on and so forth. In fact, on Desmos, you can actually switch the grid from rectangular to polar, and notice what this does. Just I'll click that off for right now. Gives me a bunch of concentric circles and lines through the origin. Very faintly. Notice those lines through the origin, a lot of them are like pi over 3, pi over 6, pi over 4, stuff we know how to deal with. Now I'm going to just look at a couple of other types of graphs. I'll use my graphing calculator, or I guess I could use Desmos too. Either way, doesn't matter. We'll deal with number plus coefficient times cosine, number plus coefficient times sine. We do plus or minus, it doesn't really matter. Okay, I think I'll do this in Desmos, might be a little bit faster. R equals 5 plus 5 times cosine of theta. Notice what I have there. I don't like that grid as much as my standard rectangular grid. So that's my standard rectangular grid. We've graphed it. I get this sort of lima bean looking shape, this bean looking shape. When the two numbers are equal up front, when this thing comes back, it just touches the origin, goes back around. What would happen if the coefficient on the cosine is bigger than the constant, something like 5 plus 9 cosine theta? Well, what I would end up with is we get an inner loop when it goes back. It won't just touch the origin, but it'll go through the origin, loop around, through the pole, and we get an inner loop. Okay. What if the coefficient was smaller than 5? Well, then as we indent, it's not going to indent all the way back to the origin. Okay. Sometimes people will put, let's do a slider there. See what's happening. Make sense? That loop gets bigger and bigger and bigger, the more our coefficient is thrown off. By the way, if we go to a negative coefficient, what'll happen eventually is we'll be pointing the other direction. Do you see that? So if we have a negative coefficient, we get the same type of shape, just pointing in the other direction. What do you think is going to happen if I change this cosine to a sine? Yeah, it's going to be up and down instead of left and right. So same thing, same concept. Negative sign points down. We have a positive coefficient, we're going up. And that loop can get bigger and bigger and bigger. When it's perfectly equal, you just go and touch the origin there. Right? So these shapes in general are called cardioids. All right? There are specific, excuse me. I misspoke. The shape where A is equal to B, where we go back and touch the origin, that's called a cardioid. All right? When A and B are equal, when those coefficients are equal, whether you have a plus or a minus, it doesn't matter. There's going to be flip-flop. Those are called cardioids. If the constant is bigger than the coefficient of cosine or the coefficient of sine, then we do not have an inner loop. We just have a dimpled version. This is called a limison. It's actually a French word. There's an emphasis there that so it's a limison. Sounds like lemon and then song almost. Right, limison. But anyways, we get a dimpled version if the coefficient on cosine or sine is smaller than the constant out front. And we have a limison with an inner loop if the coefficient on cosine is bigger than the constant out front. All of that, obviously, in absolute value. Now, I think what we'll do is we'll stop there. We'll look at some other graphs of these shapes starting next class period. And along with limicons and circles and lines through the origin, there's some other interesting shapes. Okay. All right. So I'll see you all next time.